Welcome to the CBDC video series, a way for regulators, researchers, and international organizations to learn more about stablecoin technology, design, and policy considerations.
Welcome to the third and last video of the series on stablecoins. This is the video on simulating stablecoin risks and how you could think about simulating a stablecoin environment and digging deeper into the risk factors that are important here, also important for different types of stablecoins. I mentioned it is a series of 3 videos. So the first 2 videos were an overview on different stability mechanisms. The second video was a deep dive into Celo stability mechanism, and this is now a more research-based talk about how you could simulate the risk of a stablecoin. The agenda for today, for this video is on first, we do a quick introduction and repeat a few basics from the first 2 videos, different types of stablecoins and their risk factors, since we want to simulate these risk factors today to look deeper into them. And then we talk about, in that second part of the talk, about how you could actually do this, how you could actually analyze a stablecoin, and then the third part is basically a summary of all these 3 talks on stablecoins. And as already mentioned in the first talks, there's no like common definition of what a stablecoin is, but in the end, stablecoins have like many of the features of other traditional crypto assets, but seek to stabilize the price of the coin by linking its value to that of an asset or pool of assets to some underlying. So let's start with introducing again the risk factors of these different types of stablecoins. And anyone who saw one of the first videos knows basically this overview on the different types of stablecoins. We talked about fiat or commodity collateralized stablecoins, crypto collateralized stablecoins, seniority share stablecoins, and programmatic stablecoins. We also mentioned examples like Tether for the fiat collateralized stablecoin, or Maker for the crypto collateralized stablecoin, or Celo for a hybrid or programmatic and crypto collateralized seniority share stablecoin. The first category here, fiat or commodity collateralized stablecoins, we talked about that here governance is more centralized and that audits are required on the collateral itself, since with a fiat-backed stablecoin, typically the collateral sits with some bank. There's a central entity that stores collateral, and therefore the major risk factor you would have to think about here would be the risk of the collateral being actually in place, the risk of the collateral itself, and of course the risk of that counterparty that is storing this collateral, and therefore you would have to make some assumptions about, for example, the liquidity and the counterparty risk in general of that counterparty. For all other types of stablecoin, you have typically an on-chain collateral. Therefore, it is much more transparent if the collateral is actually in place. You can check on-chain in what assets the collateral is held. You can see how the collateral is held, since it's basically held on-chain. And you can have a look at the code base governing the issuance mechanism of this stablecoin. And therefore, it is more transparent. You don't have the counterparty risk in that sense that you don't know how liquid basically the counterparty is, since everything is coded in smart contracts. However, there are other type of risk factors, and we want to talk about 2 major risk factors and how to simulate them today. These 2 major risks or risk factors are if in the case of a crypto collateralized stablecoin, or even in a seniority share type of stablecoin, if collateral is another cryptocurrency, then of course one of the risk factors is just the market value or the price risk of this cryptocurrency. And then especially for those stable coins that have a expansion and contraction mechanism. So basically for those stable coins where the supply of stablecoin can be adjusted to varying levels of demand, there also the future demand is a risk factor. So it could be that demand jumps on a certain day to a much higher or much lower amount, and therefore this jump could pose basically a price risk for the stablecoin in that sense that the protocol cannot expand or contract fast enough, and therefore also the demand is a risk factor. And this is also something we already talked about, and this is again a chart of a paper which is called an analysis of the stability characteristics of Celo. This paper you can find on the celo.org homepage, and basically in this paper we also write about that we here it is very hard to forecast demand at a future point in time. So again, tomorrow, in 1 month, in 1 year, in 30 years, we actually don't know what demand for stablecoin is, and therefore we have to assume that this demand is random. And if demand for the stablecoin you are looking at is a risk factor and demand is random, you should look into how you could simulate different scenarios of demand. And what you can see here are simulations of different scenarios of demand. What we used here, and I will talk a bit more about this later on, is a geometric Brownian motion. And you can see that we have used here different types of geometric or different means for these geometric Brownian motions. And therefore, these resulted in different scenarios, different paths. And not only the demand is random, but also the crypto market is random. And if you have crypto collateral for the stablecoin you want to look at, and this collateral is basically volatile, you also need to have a look at basically the volatility of the value of your collateral. And this is in that sense, it is a second type of risk factor. So it's basically not only the risk of being liquid enough to handle expansions and contractions, but basically also the risk of your crypto collateral losing substantially in value. And basically to estimate the likelihood of these different risks, the likelihood of the collateral dropping to below a certain threshold, or the likelihood of the demand jumping at a certain day, you want to use different types of processes to get a feeling on the likelihood of these events happening. And you could use different stochastic processes to model these risks and to come up with scenarios. So this is basically the major part of the talk today, is how could we do that? How could we analyze a stablecoin by using different stochastic processes and using these stochastic processes to model the risk factors that could affect your stablecoin you're looking at. And this is, I think, a relevant exercise for all types of stablecoins out there, since all types of stablecoins are influenced by these different risks we talked about. So when you want to analyze a stablecoin, there are different ways to do so. So you could basically forecast a future demand. You could also try to forecast future behavior of the crypto market. However, this is relatively difficult. It could be because you don't actually know what your crypto collateral is worth tomorrow. It could also be that there are some external factors that are actually relatively hard to forecast. For example, change in regulation in certain areas, or change in user behavior, or also risks or other known bugs in a certain blockchain. And therefore, all these factors are relatively difficult to forecast. So you could think about doing a scenario analysis. And when you do a scenario analysis, you could come up with like some theoretic scenarios. You could also use historical scenarios. And if you don't want to forecast the future evolution of the crypto market or the future evolution of the demand, and you don't want to do distribution fitting to historical market data, you can use stochastic processes. So basically, if you just use historical data, that is fine. However, the history of the crypto market is relatively short, and therefore also the historical available prices for different cryptocurrencies are relatively limited. And it could be that, especially during that time, the beginning of the crypto market, these prices behaved in a certain way, and it could be that this way doesn't repeat, and therefore maybe it is not enough to only look at historical data, or it's not enough to only fit your scenario analysis to historical data. And therefore, since these long-term forecasts are relatively hard, there are other ways to solve for this. And one way is basically do a simulation study, doing a simulation study can help you to think about a lot of different statistical shapes and characteristics of the scenarios you use. You could think about what is the right distribution you want to assume when simulating the prices of the different cryptocurrencies. You could, because it's relatively easy to use, you could just use the normal distribution. This normal distribution basically gives you a distribution that is fully defined by the mean and the variance around that mean. However, it could be that the normal distribution is not the best to describe, for example, crypto returns. And therefore, you could also think about a heavy-tailed distribution, which means also heavy wins or losses over a very short period of time are possible. And it could be that this distribution describes your market better. And therefore, typically for cryptocurrencies, you should use some semi-heavy or heavy-tailed distribution when doing a scenario analysis. What type of process could you do that? Could you use, and how could you do that? What you could do is basically you could do a Monte Carlo simulation. A Monte Carlo simulation basically generates values for the key factors that affect stability of the stablecoin you want to look at. For example, the key factors like demand or the prices of crypto assets that are acting as collateral for the stablecoin you want to look at. And then in the Monte Carlo simulation, you generate like these key factors again and again, and you look how does your cryptocurrency behave in these different scenarios. And one stochastic process you could use here is a geometric Brownian motion. And the geometric Brownian motion is used very widely in different types of these analysis, and different types also of market analysis of other asset classes. In the financial literature, the geometric Brownian motion is also used to simulate, for example, stock returns. It is one way how you could think about basically generating future prices of, for example, crypto assets. So what you can see here are paths from a geometric Brownian motions here on that chart to the right. These paths show you the crypto market performance in different scenarios over the course of 30 years. So you see here over 350 months of basically daily crypto market performances. They all start at 1, and then some go to extremely high values, and some basically go to 0. And if you look at the formula, how a multivariate geometric Brownian motion looks like, you can see that here on the left. So basically, the geometric Brownian motion can deliver you daily prices or daily returns for any crypto asset alone. And if you have a market of several crypto assets you want to have a look at, you could use a multivariate geometric Brownian motions. And then what you can see in this first part of that formula is that multivariate geometric Brownian motion has a mu, a expected value, and it has some volatility term, in this case here sigma or sigma squared, and then some random term that adds basically the randomness to these expected values. What you could also do is to add jumps to this geometric Brownian motion. This geometric Brownian motion then evolves from day to day. However, it could be that the whole market of crypto assets jump on a certain day by a very significant amount. And maybe the underlying distribution of the multivariate geometric Brownian motion doesn't include like these extreme jumps. And therefore you could add jump terms like you can see in this formula here. And here we have basically idiosyncratic jumps, which means it is here in this case based on a Poisson distribution, a certain jump, a daily jump of some extreme returns for a certain crypto asset on a single day for a single asset. And then there are some market-wide jumps because, for example, of some regulation change, the whole market of crypto assets jump on a certain day in an extreme fashion. And this is basically then what you need. With this formula, you can actually generate the demand paths or also the crypto market return paths for a lot of different assets. And when these are the risk factors you want to have a look at, you can use this geometric Brownian motion to look at them. What you can see here is basically a daily simulation over, again, 30 years. In this daily simulation, we've used a mu of 0. So basically, on average, we expect a 0 return. And then we also have a volatility parameter here of sigma of 0.75. And what you can basically see here is then how a geometric Brownian motion could look like over 30 years. And what you can see here is that you sometimes can find that there's a significant downward evolution of a large proportion of paths. You can see them basically, and we also have here with like the solid colored lines on that chart, we have the percentiles. And then, for example, the thick red line shows, for example, the proportion of paths that are below the 75 percentile. So for the 75% of the paths are below the red line. And they decay below a level of at least, I would say, here you can, it's hard to see, however, basically, the 75% of these paths are basically decaying towards 0 over 30 years. Why is that happening with a geometric Brownian motion? The problem for this, why we see that like most of the paths are decaying to a negative range, is that you can see some very, very positive paths on top of this chart. And to keep basically an average of 0, since we have to set the mu here to 0, and you have some very extreme positive paths on top, all the other paths, or at least the majority of paths, have to basically make up for these very positive scenarios, and therefore they decay. And this is probably something which makes it difficult to use then to analyze the crypto market. because many of these passes are now going into a negative range. Here, what you can see here is a second geometric Brownian motions. Here we used a positive mu of 0.5. Again, with a volatility parameter of sigma equals 0.75. And what you can see here is that eventually all percentiles are increasing and diverging to infinity. And therefore, also this, if you're using a positive mu, is probably hard to just use this setting, because it could lead, if you, for example, use this stochastic process to analyze demand, it could lead to a situation over a certain amount of time that all paths go into extremely positive terrain, and therefore like extremely high values, and therefore it could be too optimistic. Therefore, there's a second or another set of stochastic processes you could use. In contrast to the geometric Brownian motion, the geometric Ornstein-Uhlenbeck process has a stationary distribution, and it converges towards this stationary distribution in time. And therefore, basically, as a consequence, if you use this process, and on the right, you can see the paths of this process, and on the left, you can see the formula, how this process looks like. The big advantage of using the geometric Ornstein-Uhlenbeck process is that it doesn't decay to zero or diverge to infinity over time, but it stays stationary, and therefore, as you can see, if you look at the percentiles here, again with the solid lines, the solid red line is the 25 percentile, the 50% percentile is the green line, and the orange line shows you the 75 percentile. You can see that you don't have this behavior of converging towards zero or converging towards infinity. And I mentioned this already. One downside then is when you look at a process like this, what is probably then missing to explain an extreme market like the crypto market with like extreme jumps on a certain day for maybe every asset or just for one asset is there's like this Ornstein-Uhlenbeck process doesn't cover basically these jumps by default. However, what this process basically here has, additionally to also a volatility parameter, and you can see basically the volatility parameter in the formula here is again the sigma, and a drift parameter. This process also has a mean reversion speed, and basically you can set the mean reversion speed, and when you use a mean reversion speed of 0.03, a volatility parameter again of 0.75, and a certain drift parameter, you can now see, if you have a look at this blue line here, the 50 percentile of the geometric Ornstein-Uhlenbeck process is that at each time approximately 50% of the mass of all the scenarios is above this line, and 50% is below this initial value. And therefore, using this process basically then solves the problem of all the scenarios going to infinity or to zero. And then, as I said, you can also use this Ornstein-Uhlenbeck process with jumps to acknowledge the heavy tails that are typically observed in price distributions of cryptocurrencies. And therefore, when we worked on the stability analysis of Celo, we used a geometric Ornstein-Uhlenbeck process where we also included a jump process. We basically have additional jumps in there. In this model, we used the occurrence of a jump is determined by a Poisson process. Jump sizes are log normally distributed random variables, and this is then what you can see here. The dashed lines are the percentiles of the geometric Ornstein-Uhlenbeck process, and then the solid lines are the same process but including jumps. And what you can see is when you include jumps into your process you're using for analyzing the crypto market, then you get a wider range of scenarios you're looking at. Okay, this was like a very statistic heavy, a lot of different, we were looking at two different processes. What you should take away from this today and also from the two previous talks, I summarized in this short summary. Again, I think it is a nice way, if you think about the risk factors of stablecoins, to think about first about what type of stablecoins are you looking at. Is it, for example, backed by fiat? And when it's backed by fiat, then maybe the counterparty risk is more important, or if it's backed by crypto, then maybe the crypto collateral price risk is more important to look at. Then in the second talk of the series, we looked a bit deeper into the Celo stability mechanism, and the Celo stability mechanism basically with its two assets, Bitcoin, which is a supply stable value asset, and a governance token, Celo Gold, which is a fixed supply variable value asset that takes up the volatility of the stable asset, basically, and creates incentive for every user to expand and contract the supply of stablecoin when demand varies, is one mechanism how you could basically match supply and demand. And then the third part, or the third talk today, was on if you want to different risk factors, not only forecasting them, maybe guessing how the crypto market could look like tomorrow, but you also want to do scenario analysis and have some study on if the demand goes to a very high number or to a very low number, or if the crypto market or a certain crypto asset evolves to a very high price or to a very low price, how does this affect stability? Then you could use basically this Monte Carlo type of simulation I was talking about today. You could use different stochastic processes in the simulation, for example, the geometric Brownian motion, and for example, the Ornstein-Uhlenbeck process. And you could also think about jumps, because we are talking about a market that is not typically having a normal behavior. Sometimes there are basic decisions we are looking at here, heavy tails, extreme returns over a short period of time, and therefore maybe you could think about introducing jumps about that. If you want to read more about this analysis we did here, you can find on celo.org, you can find this stability paper, and there are also a lot of references in the stability paper to other simulations, and we hope that also on this type of assets. Okay, thank you very much. Again, I received some questions, and I also want to leave some time to briefly talk about these questions. I think we have 5 more minutes. Looking at these questions, one question is, have you considered correlation? I was talking about, like, you could simulate basically the prices of different crypto assets. You could think about a stablecoin that has as a collateral different cryptocurrencies in its reserve, and therefore you want to have you want to simulate different cryptocurrencies to simulate the stability of the stablecoin, and therefore you have to think about correlation. And in the stability paper, yes, we have introduced a correlation factor. You can easily do that by using the multivariate geometric Brownian motion or the multivariate Ornstein-Uhlenbeck process. What we did is basically we used these multivariate processes, and then we set not only a correlation between the different cryptocurrencies, we also set a correlation between demand for stablecoin and the crypto asset prices, since this could also be correlated. So again, if you want to have a look at this stability analysis, you can also find the formula on how to introduce correlation into these processes there. And then a second question was, do you simulate demand for different prices? So this is a question which is focusing on the way we simulated basically the demand here. I've showed you basically the paths of demand for a stablecoin. And what you could do is basically you could have one path for each possible price. And this demand could look like basically could look different for $1. Then it would look like if the price of the stablecoin actually depegs and goes to $1.10. But what you could also do is you could basically simulate the demand at one specific point. For example, you could simulate the demand for a stablecoin at the price of $1. And then you could assume again a demand function, and then you could basically around this simulated demand at the price of $1, you could have basically model at different prices the demand for that stablecoin. And then the last question I received is, what would you simulate to analyze fiat-backed stablecoins? This is also a very good question. With fiat-backed stablecoins, we don't have a crypto collateral. With fiat-backed stablecoins or also commodity-backed stablecoins, the stablecoin is tracking the value of the underlying, and the backing is basically in that underlying. However, this backing, as I mentioned, the collateral is sitting at, for example, at a bank. This bank has certain liquidity requirements. This bank also has a certain counterparty risk. And therefore, what you would simulate here, or you don't need to simulate basically the value of the collateral, since collateral and underlying of the stablecoin in this case are more or less the same. But what you would need to simulate in this case is basically the counterparty risk. So for example, the risk of the bank being able to pay back all outstanding stablecoin. In the end, what you would do here, then it is some form of credit analysis, since if the fiat-backed stablecoin is backed by fiat in a bank, it's basically backed by credit, and therefore the price of the stablecoin should take into account basically the credit risk of that bank. So it would be a different type of analysis, but you could also use a simulation-based approach. So again, thank you very much for listening in to these 3 talks about stablecoins. You can also find the link to the Celo chat on the last slide here. We are always happy about questions. So again, thanks a lot.